Alright, so here we are with unit number 12, our final unit, lesson number 2. And what we're going to look at here is a process called transmutation. This is a definition that you should know. And in essence, transmutation is when the nucleus of one element changes into the nucleus of another element. In other words, you're changing one element into a completely different element. And this can be accomplished in two ways. It happens naturally in nature, but it can also be done in a laboratory, which would be called artificial transmutation. So here is a couple of what we're talking about here. So let's first take a look at natural transmutation. Here's an example of it here. We're starting out with a uranium atom whose nucleus is unstable. Right? Any element with atomic number above 83 is going to be unstable. What that means, again, is that the nucleus of this atom does not like the number of protons versus the number of neutrons in the nucleus. In order to become more stable, it's going to emit particles until its nucleus is stable. In this particular case, this uranium atom undergoes what's called alpha decay, which simply means its nucleus gives off an alpha particle. An alpha particle consists of 2 protons and 2 neutrons, which the symbol is this, and this is in your reference tables. So when this atom's nucleus loses 2 protons and 2 neutrons, here's what happens. Its new mass is now going to be 234, and the atomic number, because it lost 2, is going to be 90. So now what you do is you go to the periodic table and you look up the symbol for the element that is number 90, which I believe is thorium. Let's see if this is going to work. It is not working, so we're going to forget that. So I believe it is thorium, so we're just going to put down thorium. If it is incorrect, then we will correct it. So again, it is 234 over 90. I believe it's thorium. Now, one of the things you're going to notice is you see this arrow. The arrow simply sometimes can mean just an equal sign, which helps you to understand this whole conservation of mass and charge, etc. Notice that these two numbers, the top numbers on the right side, add up to 238, which is the same as the top number on the left side. And in general, that's the way it should be. Look at this one. It adds up 90 and 90. 90 and 2 adds up to 92, which is the same thing as this side. So one of the things you're going to have to be careful of is that one of the things they will do is they will leave one of these numbers blank as an X, and they'll say, okay, what's the missing number? So they might make this blank and this blank and say, okay, what's the missing numbers here? And you have to understand that the top numbers on each side must be equal. So these are both examples. This is an example of a natural transmutation. We'll get into that more. If you look on the right side here, this is an example of artificial. Notice first thing that you have at least 2 reactants. And on this side, you had only, under natural, you had only 1 reactant. That's a way to distinguish right away natural from artificial transmutation. But the whole idea of this arrow being an equal sign is basically the same. So this new element is going to have a mass of 18, because now you're combining them, and 9, which would mean that this element now has changed into fluorine. This particular element, isotope of fluorine, has a mass of 18. So that's an example of natural versus artificial transmutation. You need to be able to distinguish between the two and to complete an equation. And we'll get into that more later. But here's examples of each. Natural transmutation includes all 3 of these, alpha, beta, and positron. They don't really ask you about positron too much. It's mostly alpha and beta. The way that the sun produces its energy is also considered to be natural transmutation. Even though it is fusion, and you see fusion is listed here, the sun, because it's doing it on its own, is still considered to be natural transmutation. And something called electron capture, which they rarely ask you about on the Regents exam. The 3 types of induced or artificial transmutation would be anytime you bombard a nucleus with particles. That's going to be artificial transmutation. And fusion and fission, and we'll talk more about both of these later on, are also considered considered artificial transmutation. If you take a look at this table, now I'm not really going to go through this because this is actually on your reference tables. As a matter of fact, it's actually on this reference table. So you can simply just take what you have here and fill it in on this table, and I'm not going to, and you still do have to do this table. The only things I'm going to run through, which is something that's not on that table, is how dangerous it is, what you need to stop that particular type of radiation. So we'll start with alpha particle, and an alpha particle is basically 2 protons and 2 neutrons. So it has a mass of 4, and the notation for an alpha particle would be this right here. That's its symbol. This is how you can make it as a notation, 4/2. Normally this one is used. You rarely see that one. And basically alpha particles can be stopped for the most part by your skin or a piece of paper. The next particle is called a beta particle, and a beta particle is sometimes used interchangeably with an electron because it is very similar. Beta particles have no mass, a -1 charge, and as you can see from this table, that would be the symbol. You can use the E with a 0 -1. Zeros meaning no mass. That would be its charge. That is its symbol there. Beta particles and positrons are very similar in some ways. They both can be stopped by a piece of cardboard or foil, tin foil, aluminum foil. They are somewhat dangerous internally and externally. The next one is a positron. A positron is a positively charged electron. It's called a positron as opposed to an electron. Still has 0 mass but has a +1 charge. Very similar to what needs to be to stop it. The last one, which is by far the most dangerous type of radiation, it's not even really a particle. Gamma rays are said to be high energy X-rays. And you can see the symbol here is sort of that funky looking Y with 0 mass and 0 charge, so they are in essence neutral. But they have a very high penetrating ability, so they can do a lot of damage to living tissue. So you'd need a lead shield or a concrete in order to stop gamma rays. That's one of the reasons why when you go to the dentist and have an x-ray, they put that apron on top of you, which is extremely heavy because it's a lead apron, so that the x-rays really don't go anywhere except in your mouth. And that's really what you need to know. The notations, again, are on your periodic on your reference tables. The masses are. The shielding is not on your reference table, so you need to remember that. They also want you to understand how those types of radiation are affected by an electric or magnetic field. And this is a diagram which shows you if you have a source of radiation and it's giving off beta, alpha, and gamma rays, and you could even say positron particles. When that beam passes between a positive and negatively charged plate, it's going to separate the particles based on their charges. So you see the positive plate is at the top, negative plate's at the bottom. So any type of radiation that is negatively charged is going to be deflected by the negative plate but attracted to the positive. So any particle that bends upward, you know, is going to have a negative charge, which would mean beta particles. Any particle that is positively charged will go towards the negative plate because opposites attract. That would be alpha, and it would also be positrons. But the path of the positrons would be somewhere in between here because positrons are not as heavy as alpha rays. They would not be as affected by the positive and negative field. The particle or the radiation that would go straight through without being affected would be gamma rays. Because gamma rays are neutral, they're not affected by a positive or negative field. Would be the same thing if you put neutrons. A beam of neutrons would travel basically the same path as the gamma rays, and electrons would travel the same path as the beta particles, and protons would travel the same path as the alpha particles. And it kind of, and I'm not going to go through that video because it's going to take a while, and it just kind of goes through and explains what we just talked about. And that's it for this one.